So today we're going to be talking about the small signal analysis of a differential pair amplifier. So the first thing that I'm going to do is I'm going to draw the small signal model for a differential pair, right? So just as a reminder, our differential pair amplifier is going to look something like this. So here we have some collector resistance. Let's start with the BJT and then we'll go from there. V out 1. Here's V out 2. V in 2. V in 1. Don't know why I put that line there like it was a MOSFET. Let's fix that. Tail current, IEE. This is transistor Q1, transistor Q2. All right, so we're going to be doing small analysis. So let's say that we are applying half of some small signal differential mode input voltage, lowercase VID, on the V in one side, and the other half we're putting over here on the Q2 side. So this will be negative 1/2 VID, right? All right, so we're going to draw our small signal model for this thing, and it's going to be fairly large just because there's a lot of things going on here. So I'm going to start here. So here's my small signal input voltage, VN1. Here's R pi 1 and VBE 1. GM1, VBE 1 in parallel with some resistance R0 1. And then this is going to seem a little odd, but I know, so let's see. So this is the base of 1. This is the emitter of 1. So this node right here is going to be the collector of 1. And so what I'm going to do is I'm going to draw my RC like so. So it's between the collector of 1 and AC ground, which is still correct. It just looks a little different than I've been drawing it. And it's just from a space perspective. And then my small signal output voltage, V out 1, is here. Now I'm going to draw effectively this exact same thing, but mirrored on the other side, right? So this is going to be R0 2. GM2, BBE2. Here's the voltage VBE2, which is across R pi 2. Here's my input signal VN2. So this is the base of 2, the emitter of 2, the collector of 2. So here's RC. Here's V out 2. And we know that our emitter nodes for both of our transistors are tied together. So I'm just going to connect those by a line. And I'm going to add something in here because it may not be super obvious. The voltage at this node here in the middle, where our emitters are tied together, is floating as far as we're concerned right now. What I mean by that specifically is if we look at our large signal model, there is a DC current source between that node and ground, which on our small signal model is going to look like an open circuit. So I'm going to call this voltage Vx. And the first thing that we're actually going to do in our analysis of figuring out what's going on is to figure out what the heck Vx is, if we can, okay? So in order to facilitate that, I'm going to write a Kirchhoff's voltage law equation around both of my input loops, okay? So what I mean by that specifically is I'm going to do one on this side. So I'm starting at ground, going around this path like so. And then I'm going to do something similar on this side. So starting at ground and going to ground here like so. So what I'm going to have on the left-hand input side or the transistor Q1 side of things, it's going to look like negative VN1 plus VBE1 plus Vx is equal to 0. And I could rearrange that to say that Vx is simply going to be VN1 minus VBE1. We okay with that? Very similarly, I would have negative VN2 plus VBE2 plus Vx is equal to 0. And so now I can say that Vx is simply VN2 minus VBE2. All right, so let's apply Kirchhoff's current law at node X now, okay? So if we're applying KCL at node X, we're going to have a whole heck of a lot of currents that we're going to be dealing with here, right? So let's start on the left-hand side of the circuit. And let's look at current flowing into node X as positive. So we're just summing up all of the currents that are flowing into X, okay? So we're going to have a current of VN1 minus Vx divided by R pi 1 flowing in. So that's the current flowing through the resistor R pi 1. We're going to have a current of GM VBE1 flowing in. So GM1, VBE1 we just figured out effectively is VN1 minus Vx. So we'll go ahead and make that substitution. We are going to have a current flowing through that resistor R01. So that's going to look like V out 1 minus Vx over R01. And now we're going to have effectively the exact same set of currents flowing in on the right-hand side. So that's going to look like V out 2 minus Vx over R02 plus GM2 VN2 minus Vx plus VN2 minus Vx over R pi 2 is equal to 0. So before we start messing around with this too much, is this okay? Nothing more than application of Kirchhoff's current law at node X, where we're just saying all of the currents flowing into node X have to sum together to make 0. All right, so let's lump some things together, okay? So I can see that I have a VN1, oh, actually, let's make an assumption here, okay? So if Q1 and Q2 are perfectly matched, then R pi 1 has to equal R pi 2. So we'll just call this R pi. GM1 would have to equal GM2. So we'll just call that GM. And R01 would have to equal R02. So we'll just call that R0. So if those transistors are perfectly matched, that should be the case.
Dumb question, but what is the final expression?
We're trying to figure out what Vx is for right now, because knowing what that voltage is going to be critical to us understanding how this circuit works. Okay. So under the constraint that our transistors are perfectly matched, and we're not ready to not match them just yet, because that's actually what we're going to cover on Friday. So let's see what reduces out. Okay, so we have a Vn1 over R pi 1. We also have a Vn2 over R pi 2. Since the R pi's are the same, this should look like Vn1 plus Vn2 divided by R pi. The other part of those expressions is going to give me a negative twice Vx over R pi. Then I have a GM times Vn1. And I have a GM times Vn2, so I can add those guys together. And then I'm going to have a factor of negative twice GMVX. Then I'm going to have a Vout1 plus Vout2. Over R0. And then I'm going to have minus twice Vx over R0. And all of that is equal to 0. So that's just me rearranging things under the constraint that my R pi's are the same for both transistors, my GMs are the same for both transistors, and my R0s are the same for both transistors. So are we all still okay? All right, so way up here, I stated that Vn1 was half of my differential input voltage, and Vn2 was negative half of my differential input voltage. So what should Vn1 plus Vn2 equal? 0, which means everywhere we see a Vn1 plus a Vn2, that term goes away. So this guy goes away, and that guy goes away. And now we have things in terms of just Vx and Vout1 and Vout2. Okay. So in order to figure out the relationship between, or to give us a different relationship between Vout1, Vout2, and Vx, we're going to apply Kirchhoff's current law at our collector nodes, right? So KCL at the collector node of transistor 1, which is this node right here, is going to give us put this here, KCL at node C1. We're going to have Vout1 over RC. We're going to have, so that's the current flowing out of that node. We're going to have GM VBE1 flowing out of that node. So GM times Vn1 minus Vx. And then we're also going to have a current of Rout1, excuse me, Vout divided by R0. Oh, actually, I should have a Vx there as well, sorry. So here, for the sake of having positive signs everywhere, I'm just saying current flowing out of C1 is positive. So if we did current flowing in, that would be fine. We would just have a negative sign in front of everything, which isn't going to change the relationship at all, because it's just multiplying that by -1 gives us the relationship that we had. So just to be clear here, this was the first current term, this was the second current term, this was the third current term for KCL at C1. Now we're going to do the exact same thing at C2. And we should get effectively the same thing. So we should have V out 2 over RC plus GM VN2 minus VX plus V out 2 minus Vx over R naught is equal to 0. So we're going to do something a little wild here. I'm going to add these two KCL expressions together. So why can I do this? Well, exactly right. They are both equal to 0, and 0 plus 0 is still 0. So what's the harm in me adding them together? There is literally none. So when I add these together, I wind up getting GM VN1 plus VN2, which we know that's going to go to 0. I'll cross it out here in a minute, minus 2 GMVX. I'm going to have a V out 1 plus V out 2 over RC. I'm going to have a V out 1 plus V out 2 over R naught. And I should have a minus 2 Vx over R naught is equal to 0. Everything look okay there? So let's go ahead and cancel that guy out, since we know that Vn1 plus Vn2 is equal to 0. And what we're going to do now is we're going to solve for V out 1 plus V out 2 in terms of Vx, right? So V out 1 plus V out 2. Let me put this in parentheses. So I have a factor of 1 over R naught and a factor of 1 over RC here on the left-hand side. I'm going to move my Vx terms over to the other side. So that's going to look like twice GMVx plus twice Vx over R naught. And from here, I can say that V out 1 plus V out 2 is equal to twice GMVx plus twice Vx over R naught. Times 1 over R naught plus 1 over RC to the negative 1 power. I'm about to replace that thing because that's nothing more than literally R naught in parallel with RC, right? So let's just put it in like that because it's a little less gross. All right, and now I can substitute in this relationship for V out 2, or V out 1 plus V out 2 back into this guy up here. Okay. So let's see what's going to shake out of that. So we're going to have negative twice Vx over R pi. So let me just scroll up here. So we took care of this guy right here. Negative twice GM times Vx. Negative twice Vx over R naught. And then now we have the V out 1 plus V out 2 over R naught. Sorry. Taking a moment here because I'm trying to figure out what the hell happened. To my negative signs in my notes. We'll make it work. All right, so sorry, now I'm doing, so I have that term, I have that term, I have that term. So now I'm gonna have plus V out 1 plus V out 2 over R naught. So that's gonna look like plus 1 over R naught times 2 GM VX plus twice Vx over R naught. This whole thing multiplied by R naught in parallel with RC is equal to 0. So let's factor out Vx from this thing. So I'm going to do my positive terms first, right? So I'm going to have a twice GM over R naught times R naught in parallel with RC. So that is this guy right here, where I've also included this contribution. Then I'm going to have a twice R naught in parallel with RC over R naught. So that's taking this guy into account. Now I'm going to have a minus 2 over R pi minus twice GM minus 2 over R naught. Actually, that guy right there should be R naught squared. Yeah. Is equal to 0. So what is this expression right here in front? Vx is 0, right? So the only way for this to be true is either everything in the brackets is equal to 0, which if we put everything in terms of a common denominator, we would find out will not be true. It's just going to be a bunch of gross algebra for no point whatsoever, or Vx has to be equal to 0. So even though that node is floating from a small signal perspective, meaning that it's representing that there's that open circuit there from the independent current source on a small signal. Because this circuit is perfectly symmetrical, it's going to look like it was connected directly to ground. Anytime that we have a symmetrical circuit, which will happen pretty regularly, especially when we're dealing with things that are based on differential pair amplifiers, we can just treat that emitter node as if it were connected to ground and go on about our analysis. Even if it's not 100% symmetric, but it's very, very close to symmetric, we should know that that voltage at that node should be very close to ground. Okay, and we'll talk about that more in a couple of days. So what that means is that we can actually split our small signal model into two parts and do our analysis that way, right? So on this side, I have half of my differential input voltage. Here's R pi VBE1. GM VBE1. R naught. Actually, I don't need the one there. Sorry about that. I'm going to tie this emitter to ground because we just figured out that emitter node is essentially at ground. Here's RC. Here's V out 1. Let me put the same thing on the other side. R naught. GM VBE2. R pi VBE2. Oh, shit. V out 2. RC. Negative VID over 2. And this guy right here is also at ground. So let's look at just the left-hand side. If I look at just the left, yes.
I would pick out from our, did you ever change it where the
So we'll get into that in just a second. So you're saying like, what if I didn't put half on one side and half on the other? What if we put everything on one side and none on the other or something like that? Yeah, we're about to sort that out here literally right now. So right now we're working under the, I want to say it's a constraint, but it's not a real constraint, where we're decomposing any input signal into a common mode signal and a differential mode signal on each side, which we talked about at the very, very beginning. And so we're looking at what's going to happen on each side of the amplifier. And then here in literally just a moment, we're going to see that it behaves very similar to something that we've seen before. And so we could do an analysis where we put all of the differential input mode signal on one side, and we'd wind up getting the exact same results. So we're about to see that.
But isn't our assumption that it's ground in front of the
so yes and no, and let me explain what I mean by that explicitly. Large signal. So we're talking about this as a small signal amplifier, right? So large signal, that means that we have the exact same voltage applied, the exact same biasing voltage applied on both sides. So this is perfectly symmetrical. And then we're putting a small AC perturbation on top of that, right? So realistically, this shouldn't push things off of where that is by a huge amount, even if that assumption isn't true. Yeah. So if we apply our input signal of VID over 2, what should V out 1 be? So let's go back to this really quickly. We're looking at the left-hand side. What type of amplifier is this the small signal model? Common emitter amplifier, which has a voltage gain of what? negative GM times R naught in parallel with RC. So we should be able to see from this guy that V out 1 is just VID over 2 times negative GM R naught in parallel with RC, which is going to be, just rearranging this slightly, negative 1/2 GM R naught in parallel with RC times positive VID over 2. When we look at the right-hand circuit, oh, because I was not paying enough attention, thank you. Thank you for that, Brody. About to make a terrible mistake. So what's happening on the right-hand side of the circuit? Pretty much the same damn thing. It is also a common emitter amplifier. So now we're going to have negative 1/2 or negative VID over 2 times that same negative GM R naught in parallel with RC, which should equal positive 1/2 GM R naught in parallel with RC times VID. Right? So let's say that our differential mode output signal, VOD, is V out 1 minus V out 2. That's going to give us negative 1/2 GM R naught in parallel with RC times VID minus 1/2 GM R naught in parallel with RC times VID. So taking those two identical terms together, we're going to get rid of the factor of 1/2. Negative GM R naught in parallel with RC times VID, and our differential mode voltage gain would just be the ratio of VOD over VID is negative GM R naught in parallel with RC, which means effectively, as long as we can analyze half of the circuit, we know how this thing is going to behave, right? So we no longer need to even care that it's a differential amplifier, because it would be the exact same thing as if we had just applied all of our input signal to one side and applying ground at the other input. So it doesn't matter what the ratio of how much of the differential mode signal is applied to one side or the other side, we're always going to get this result. Does that kind of answer your question? Yeah. All right, so what if we wanted to, now that we have an understanding of the small signal behavior of a differential pair amplifier, what could we do in order to boost the voltage gain of a circuit like this? Make RC bigger. Okay, so how might we accomplish that? Make it a transistor. 100% correct. Right? So we might have something that looks like this. So I'm drawing this in this way. The bases are tied together is what I'm trying to illustrate here. There's just not a nice looking way to draw this. Okay. So we have some transistor Q3 here, some transistor Q4 here. Their bases are tied together. Here's our supply voltage. Oops, I did not mean to tie their sources together. There's V out 1, V out 2. VN1. VN2. Tail current source. IEE. What should our differential voltage gain for this circuit be? Hopefully you can do this literally just by inspection. Sure, absolutely right. So literally just negative. So here we're going to be explicit. I'm going to call this Q1 and Q2. So negative GM1, or we could call this GM sub N for the NPN transistors, times R naught for the NPN transistors in parallel with R naught for the PNP transistors. Absolutely right. Nothing remotely difficult. We could do any kind of variation that we can think of. As long as it's symmetrical, it's always going to work out this way, right? If we wanted to get crazy, we could actually replace transistor Q1 with a cascode amplifier instead. We would need to replace transistor Q3 with a cascode current source, but we would have still a differential pair. Its gain would be incredibly large because the cascode's gain is so much larger than just the common emitter. But as long as our circuit is symmetrical, it's still going to behave in exactly the same way.
Replace one.
So cascodes on both sides, yeah. Then our differential mode voltage gain would just be the gain of a cascode amplifier. Yep. All right, so what do you guys think is going to happen if we were to replace our BJTs with MOSFETs? The exact same thing. All right, we're done for the day. What's the point of this circuit? So the overall point of a differential amplifier is to suppress noise, okay? So as long as we are applying noise to both of the inputs, it gets canceled out because that is a common mode signal. It's only the differential mode signals that are getting amplified here. So if we apply the exact same voltage, so if we applied positive VID on both sides, we can see very easily we're going to get rid of this negative sign isn't going to cancel out. I'm pointing at it with my finger, not my cursor, so you can't see it, but that negative sign would go away. And so when I subtract those two things, it's literally just going to give me 0. So we are attenuating all common mode signals and only passing differential mode signals. Now, I'm getting a little bit ahead of myself here. We're not going to go into this analysis whatsoever, but like right now, the circuit that I have drawn has a differential mode input and a differential mode output. We could convert this into something that has a differential mode input and a single-ended output. One way to do that would be literally to just ground one of the outputs so that we only care what's going on with V out 1. Why would that be problematic? We're going to get exactly half of the gain of the circuit because the other output is always tied to 0. There's a way around this where we load this guy with a current mirror. So instead of what we have right there, if we had something like this, we're not going to analyze this yet. This will be the last topic that we talk about. We take our V out here. Here's VN1. Here's VN2. Let's call this, for the sake of argument, Q1, Q2, Q3, Q4. Hopefully, we can recognize that this thing up top here is nothing more than a PNP current mirror, right? Anybody have any idea what the name of this whole circuit is? We usually call it an op amp. This is a single stage op amp. We take a differential input voltage and convert it into a single-ended output stage. Now, this is a really shitty op amp in as much as it can only drive capacitive loads because of what its output resistance is. So we might chain this into another amplifier to provide more voltage gain and give us a better output resistance. And we probably would wind up putting a third stage in that's literally just to increase the voltage swing. It's what's commonly called a push-pull amplifier. And it just helps the output get closer to the supply rails. So that's a single stage amplifier. We might do something like this. I'll just do the second stage here. So like we're getting ahead of ourselves, but I'm having fun, so we're just going to keep going for a little bit. So as this circuit is drawn, on the DC side of things, we have a large DC offset. So if we want to make this a good op amp capable of the largest possible swing on the output, what does our second stage need to be? So we want gain, but we also want to drive the DC level back towards ground. So a PNP amplifier. So if we do an NPN differential pair, we need to chain it into a PNP amplifier of some sort, and we'll bring that DC offset back closer to halfway between VCC and ground. Or if instead of having ground here, we have some VCC minus, we would pull that DC offset closer to 0. So you might have something like this. So let's see. So let's bring that up here because that's the source. R C, or not source, emitter. And now here's the V out for this stage. We got more voltage gain and we pulled the DC signal level down. And so we can keep doing things like that over and over again to get more and more gain. But realistically, we wouldn't just use a simple common emitter amplifier for every part of this thing. We'd probably use cascodes here and there in order to just give us more gain without having to have 15 stages. Yeah. Yes. So what the current mirror is doing is it's serving as an active load effectively. So what I mean by that specifically is we know that looking into the input terminals of current mirror, we're still going to see a small signal resistance of R0 P. Well, we're going to see R0 P looking into Q4. We're going to see R0 P in parallel with R pi P in parallel with 1 over GMP looking into Q3. But tying those bases to that node on the left-hand side. So this diode connection right here, as opposed to just tying the bases together, winds up actually giving us the exact same voltage gain as if we had not grounded, like, trying to think how to explain. We're gonna have to analyze the circuit fully, I think next Monday. But it's gonna wind up giving us the exact same voltage gain as our differential pair has without grounding one of the outputs. So it gives us a single-ended output, but gives us the exact same gain as if we had the double-ended output, except that it actually flips the gain polarity. So instead of this being an inverting amplifier, it winds up being a non-inverting amplifier. But anyway, but we'll get into all the details of that in a couple of days. So small signal analysis of the differential pair, way, way easier to follow what's going on than the large signal analysis, in my opinion. All right. So any other questions before I go hide in my office and make out tests? Yes. Mm-hmm. The reason why I added them together instead of setting them equal to each other is because I needed to have things in terms only of V out one plus V out two. So if I subtracted things, I'm going to wind up getting things in terms of V out one minus V out two. So the relationship isn't really going to change. It's not doing what I need, because my ultimate goal was to get rid of all of the VN ones, the VN twos, the V out ones, the V out twos, and just be able to solve for what VX is. So that's why I did it that way. Mhm. In a sense, what we did here is the exact same thing as what we do when we're doing KCL at a supernode. There's no voltage source or anything, but we're just saying, I'm doing KCL over here and KCL over there and adding those results together, which is exactly how KCL worked at a supernode way back from circuit one. Yeah. All right. See you guys later, but hopefully not today.